It's been said that in order to understand recursion, you must first understand recursion. Understand recursion. Understand recursion. Hi guys. I want to talk about recursion in this video. Recursion is a simple concept that is surrounded by a lot of mystery, unnecessary mystery. As far as programming goes, recursion is the ability of a computer language to call itself. So a function created in that language can call itself and therefore repeat that same function over and over and over, usually with different data. When we think about the design of recursion and the purpose of recursion, one of the first things we realize is that all of the problems that we tend to solve with recursion can also be resolved with simple repetition. So why do recursion? Because recursion, despite all this mystery that surrounds it, also simplifies our problem. In fact, a better definition of recursion is dividing a project or a problem into smaller and smaller pieces until the problem is resolved. What we're going to find as we look at different examples of recursion is that once we understand the process that the program is going through, we're going to find out that we have vastly simplified the big body of our code. So let's take a look at an example and see a figure of what's going on in memory when we process recursion or process a recursive function. Recursion makes a little bit more sense when we can look at it right in front of us. And here is a recursive function called fact. It is a factorial processor. And you can see the example of what we've been talking about where the function calls itself in that the last line of the function there, factorial calls the function factorial or fact, passing on a new parameter value. That will continue until it hits the base case, which is if num equals 0. When we get to that point, then we will be done and the return process will begin. So let's walk through the process of what happens as this recursion occurs. The first thing that happens is that the original caller, the first call to fact, gets put on hold. It remains in memory. All of any internal parameter values or variable values hold their value. It sits on the stack. And a new copy of the factorial function is placed into memory. So that new copy of the function gets pushed onto the processing stack. It's all new variables, all new, whatever the new parameter value is, everything. And so that process goes. It then tests itself against the base case, and if it doesn't meet the base case, it continues forward and begins to process anew. And so maybe another copy and another copy and another copy. So many copies can be placed on the stack as long as memory allows that to do so. This keeps going until the base case is reached. Once the base case is reached, then the return process begins. That last call returns back whatever value is set in the base case, and then that initiates the return of the one that preceded it, and that initiates the return of the one that preceded it, and so on and so on and so on, all the way back until you get to the original caller, and then the result of all of that recursion is passed back into your program. Now, one of the things we want to remember about recursion is that the base case, or the stopping case, whatever you want to call it, is critical. If you don't have a stopping case, or if your recursive function never hits that stopping case, what's going to happen is you're going to get into an infinite loop. And because each time that that recursive function is processed, it's blocking out a little bit more memory, a little bit more memory, a little bit more memory, you're going to find out that you quickly run out of memory resources and your machine's going to crash. So that base case is absolutely critical. The first thing that we do is a recursive function that doesn't return any values. All it's going to do is take an integer value, so you see on this screenshot there 1, 2, 3, and it's going to write them out vertically, but it gives us a good glimpse into the process of recursion. When we look at this function, there are a couple of things we want to note. It's slightly different from the factorial example. Our base case is if n is less than 10, so whatever that integer value is that the user passes us as a parameter value, we test that. So writing vertically means that every 10 in the decimal system is going to be written out as a separate number. So 123 goes 1, 2, 3. So if the user passes us 9 as a parameter value, we would simply write the 9 and be done. There's no recursive call. So in our example, the user has passed 1, 2, 3. And so the base case is not going to fire, and it is going to make a recursive call. So looking at our code, we go down and we see that it says write vertical n divided by 10. This is integer division, so it's going to drop any decimal component of the number, and it is going to call itself. Note that the cout statement that follows that write vertical call is not processed because we haven't gotten there yet. It will only process when the write vertical call reaches the base case and begins to complete. So this function call has not completed yet. It's just on hold on the processing stack. So you see initially we pass 123. 123 is not less than 10. And so we call write vertical again with 123 divided by 10. That gives us our second call. We're actually going to call write vertical with the value of 12. 12 is not less than 10. We call write vertical with 12 divided by 10. And that is going to result in a third call to write vertical. Now we have reached the base case. So we went from 123 to 12 to 1. All of these instances of the function are sitting on the processing stack. We've reached the base case, and now at the base case we can output or see out the value of 1. So we output that to the screen. That will conclude this instance of the program, and so it will return, it will pop that off of the stack, and then it will return back to write vertical. And then you see that once I have completed the function call, now the cout statement can begin to process, and it will go cout 1 in the base case, and then cout 2 because 12 mod 10 is going to put the 2 out on the screen, and then 123 mod 10 is going to output the 3 onto the screen. And so that gets us the vertical 1, 2, and 3 as each of these things is popped off the stack, written out to the screen. So the 1 would come first, then a new line would be processed, 2 would come second, a new line, and then 3 would come third, and output that out to the screen. So a real simple example of recursion, a couple of things that we've learned. We learned that each time that a recursive call is made, a new instance of the function is placed into memory. Now, that will get you thinking right away, well, what happens to that memory? Well, if you make a sufficiently large recursive call, you can quickly gobble up all of your available memory, all of your stack. And so Recursion could cause you a problem. It's unlikely, but you as the designer have to evaluate whether or not that's going to be a situation that you have to face. Probably in that case, it's not going to be an issue. Now, example 2 gives us a little different view. This is a function that is going to return a value. So power is going to exponentiate a value. So we're going to go 3 to the third power, I think, in the example here. We'll get a look right away. So in this case, our base case is at the bottom, it's return 1. And otherwise, as long as that number is greater than 0, we make a recursive call. Now I want you to notice that the return statement, where it says power and it calls itself again, has 2 parts to it. The return obviously won't occur until the instance of the function completes, but the equation, the multiplication that's inside of the parentheses, will also not process until the value gets returned from power. So keep that in mind as we look how this is laid out. So we call in this example the function power with 3 to the third power. And so because that doesn't meet the base case criteria, it says call power again with x, so 3. But in this case, we say n minus 1. So 3 minus 1 is 2. So we process that. The multiplication is a part of the equation, but it's not processed yet. And again, it doesn't reach the base case. 3 minus, or n minus 1 is going to be 2 minus 1 in this case. So now it's down to 1. And finally, it will reach the base case. So 3n 0. So what we do is wind out by subtraction all the way out to 0. And then we're going to use, starting from that 0, to the return values as they get popped off the stack to walk our way back to the exponent value that we're going to process. So when the base case is reached, it returns 1, which begins the multiplication process. The value, now power has completed, it has returned, it has popped off the stack, and now that multiplication call can be completed. So it's going to be 1 times x, which is 3. So 1 times 3, and then that gets returned. Now the second instance gets popped off the stack. And so it's 3 times 3, and then 9 times 3, and finally we get the 3 to the third power, 3 times 3 times 3, which is 27. So in each case, because we are returning a value, this cleans up after itself. It walks its way out by subtraction, and then walks its way back by returning a result step by step by step by step, and we end up with the 3 to the third power result that we're looking for. So in this case, there's no memory cost so long as we have sufficient stack space to write all of the instances out as we walk our way back from the initial parameter value. This last example is a little bit more complex, but it's something you can use to look forward to a little bit more complex programming problems. We understand the binary search. We take an ordered list, and as we search for a value, we subdivide that list. We divide it in half, and we ask the question, could the value I'm looking for be in the top half or the bottom half of the list? We discard whichever half could not contain the value, and then we return again. Divide the list, could it be here, could it be here? Divide the list, could it be here, could it be here? And finally, we either find it or we run out of list. So it makes a good candidate to be used for a recursive process, because in that recursion, I start by passing the beginning and ending subscript of the array that contains all these values, and then I can make the same function call with the new subdivided, which is either 0 to midpoint or midpoint to end point, whichever way the function works out. So as we look at this, let's keep that in mind. It simplifies the function now. Now our binary search function is much simpler because all we have to do is recall the same function. We don't have to have any repetition structures built into this because the repetition is going to be taking care of itself. What I want you to notice about this example, though, is that there is no return value. And as each of these instances of this function are placed into memory, the memory stack is going to get filled up. And there is nothing in this function, the example of the function, to clean up that memory structure, that memory stack. And so what you would do is, if you were going to use recursion to solve a problem like this, is you would also have to create a process to manually handle the garbage collection if you're programming in C++. Other languages would take care of this for you, but C++ does not have automatic garbage collection. Okay, so we have the code in front of us. We understand the algorithm in and of itself, so let's go in and walk through a couple of recursive calls. So the first time we call the function, we see that we're going to call it with 0 and 9, the beginning and ending. 63 is the value that we're looking for, and then the found and the location. Those are not relevant to our discussion right now. All right, so we call, we pass the array in there, and the first thing that it's going to have to do is subdivide the list. So it splits the list, and it evaluates where 63 could possibly be. Well, it can't be in the 15 to 57, so we're going to discard that. So we're going to make a recursive call to the search function, and in this case, we're simply going to pass 5, the midpoint, and 9 in order to make the function call. So have we found the value? If we have not, we walk the same process again. We divide it. We break it down, and then we make a further division. So we've broken this, and we continue that on until we finally find the item. So the binary search, once you understand that algorithm, now you can begin to look at it in a recursive process. It is going to take the entire list and simply repeat the process of subdividing the list until you either find the value that you're looking for or you're done looking at the list. Recursion is a useful tool. It can be a challenge to understand at first, but once you understand what's going on in memory and how your processing is being put on hold, it makes a lot more sense. You can take any of these examples in the video and you can put them into your compiler, and you can actually walk through with the debugger and see how all of this is working. So you saw in those examples that every single call to a recursive function does one of two things. It either reduces the size of the problem, or in the final case, it solves the problem. As long as we remember both of those keys, designing a recursive function is easy.